Hi and welcome. In this video, we're going to review antibiotic coverage with the goal of helping you develop a framework for organizing which drug is used for which bacterium. We are going to focus only on antibiotics, so no antifungals, antiparasitics, or antivirals will be discussed. Also, we are not going to cover mechanisms of action or side effects. In focusing only on drug coverage, I want to strongly emphasize that what we're going to show here are generalities, not specifics, and not written in stone. Please view this as it is meant to be, an organizational scheme for second-year medical students, not clinical guidelines. So, to start, we're going to review antibiotics from 2 points of view, that of the bacteria and that of the antibiotics themselves. So let's start with the point of view of the bacteria. As you know, there are many ways you can classify bacteria, but for our purposes, we are going to categorize them in 5 different ways. The first classification is intracellular versus extracellular. For intracellular bacteria, there are 2 things to remember. First, you are not going to use beta-lactams because these drugs won't penetrate the host cell. Second, you are going to use doxycycline or a macrolide. These are broad-spectrum drugs, so give you good coverage, and they can find their way into the infected host cells. For extracellular bacteria, the opposite is true. The fact that there are a wide range of beta-lactams that collectively cover a broad spectrum of bacteria, coupled with high level of specificity, mean that these drugs are typically used as the first-line antibiotics for infections caused by extracellular bacteria. Our second classification scheme is, predictably, gram-positive versus gram-negative. For gram-positive bacteria, we can subdivide these into drug-sensitive versus drug-resistant species and strains. For those bacteria that have not acquired antibiotic resistance genes, we are going to start with beta-lactams, including natural penicillins, the penicillin V and G, anti-staphylococcal penicillins, and first and second generation cephalosporins. If, however, you have an MDR gram-positive or multi-drug resistant gram-positive, then we need to think differently. We will start with vancomycin, and from there move into linezolid or daptomycin as determined by an antibiotic resistance report. But remember, vancomycin, linezolid, and daptomycin are not first-line drugs in the absence of high-level suspicion of drug resistance. As far as gram-negative bacteria are concerned, aminopenicillins are a good choice as a first-line treatment. Otherwise, there are only really 2 drugs that are commonly used that exclusively target gram-negatives, the monobactams such as aztreonam and colistin. For colistin, think coli as in E. coli, which is of course gram-negative. Both of these drugs, aztreonam and colistin, are quote-unquote big guns that are only going to be used in the hospital setting when no other drug will do. The third classification scheme we can use is aerobic versus anaerobic. This is not that complicated since there are no drugs specifically aimed at aerobes and facultative anaerobes. So therefore, it's pretty much open season on these bacteria. On the other hand, anaerobic bacteria respond to a more limited number of drugs, and among these, some are better than others. The 3 you should keep in mind when thinking about anaerobes are metronidazole, which is anaerobe specific, and clindamycin and the cefamycins, both of which cover anaerobes and aerobes. The cefamycins are typically lumped with second-generation cephalosporins, but they differ slightly in structure. This is not something you need to worry about, so for your purposes, just consider them second-generation cephalosporins. They include cefoxitin, cefotetin, and cefmetazole. One way to remember these is that these are the only drugs within the first and second generation cephalosporins that have T's in the name. We will talk more about the cephalosporins shortly. The fourth classification scheme is whether or not the infection is community or healthcare acquired. If community, there is no a priori reason to assume MDR strains are involved, and you can default to other classification schemes. By contrast, all healthcare acquired infections, or HCAIs, are MDR until proven otherwise. This means you are going to roll out the serious drugs. Remember, if treating empirically, you always want to cover both gram-positive and gram-negatives. So for gram-positive coverage of healthcare-acquired infections, you will use vancomycin, while a potential gram-negative infection would be covered with something like piperacillin tazobactam, meropenem, or amanobactam, like as Trianam. More about these in a bit. Importantly, for these infections, you need to get a specimen off to the lab, ideally before antibiotics are given, so you can narrow coverage with the best and hopefully cheaper drug for the identified microorganism. The last classification scheme is simply the bacteria that cause UTIs. The deal here is that you need to treat with drugs that concentrate intact in the urine. Fluoroquinolones now carry black box warnings and should never have been used in the first place to treat simple UTIs, so don't even think about giving them to a healthy outpatient with a garden variety UTI. Instead, your choices are TMP-SMX, nitrofurantoin, and phosphomycin. We will mention TMP-SMX later because of these three drugs, it is the only drug that reaches high enough concentrations in the blood and tissue to be useful outside the setting of UTIs. Now we're going to switch gears and do the heavy lifting and think about drug coverage from the point of view of the antibiotic itself. We are going to spend most of our time two groups of drugs, beta-lactams and protein synthesis inhibitors, and then wrap up with a few comments about some of the others. So here goes. Of course, we're going to start with the beta-lactams. We can divide beta-lactams into four groups: penicillins, cephalosporins, carbapenems, and monobactams. Let's start with the oldest group, the penicillins. Although we don't commonly think of it this way, we can divide penicillins into generations like we do with the cephalosporins. Of course, the natural penicillins, V and G, are the oldest. At this point, they are pretty much used only to treat some streptococcal infections and syphilis. Next on the list is the anti-staphylococcal penicillins. These include methicillin, which is no longer sold, much less used, nafcillin, oxacillin, and dicloxacillin. So let's give a nod to these drugs. These drugs are used to treat infections caused by bacteria that produce beta-lactamases that degrade other penicillins, in other words, the natural penicillins. Nafcillin and oxacillin are considered narrow spectrum for gram-positives, while dicloxacillin has a broader spectrum of activity covering some gram-negatives. Next in the journey of penicillin development was an attempt to cover more gram-negatives, and this was accomplished with the aminopenicillins, which conveniently start with the letter A, amoxicillin and ampicillin. You have probably seen lots of amoxicillin prescribed in your peds ICE office. Oftentimes, it is paired with the beta-lactamase inhibitor clavulanic acid, or clavulanate. This drug combo is also known as Augmentin. Ampicillin is available paired with the inhibitor sulbactam for parenteral or IVIM use. Recall that unlike gram-positives, gram-negatives have only one way to be resistant to beta-lactams, and that is to make a beta-lactamase. So it makes sense that these two broad-spectrum, widely used beta-lactams are available in combination with beta-lactamase inhibitors. There is only one bacterium that I can think of that is always associated with one of these drugs, and that is Listeria monocytogenes, which is treated with ampicillin. Finally, the fourth generation penicillins are the big guns, or extended spectrum penicillins, piperacillin and ticarcillin. They are called extended spectrum because they cover even more gram-negatives than the aminopenicillins, including some Pseudomonas aeruginosa strains. They also have good coverage against streptococci and staph, but importantly, they do not cover MRSA. Although both are inherently more resistant to beta-lactamase cleavage than other penicillins, they typically are given paired with a beta-lactamase inhibitor. So piperacillin is produced in combination with tazobactam and is known as pip-tazo, while ticarcillin is made in combination with clavulanate. You will see pip-tazo used more because it has broader coverage than ticarcillin. Okay, on to the cephalosporins. As you know, these are commonly referred to by generation, probably because each generation has so many drugs, it's way easier to talk about generation than the specific drugs. Of the 5 generations, the biggest generality is the following. First and second generation provide good coverage of gram-positives. Third and fourth generation cover gram-negatives as well, but at the expense of some gram-positives. To a first approximation, you can further differentiate between first and second generations in that the second generation includes the cephamycins, so there is better anaerobe coverage, but at the expense of some of the aerobic facultative anaerobic gram-positives. The true second-generation cephalosporins conform to our gradient of increased gram-negative coverage as the generations age, so more gram-negatives than first generation with equivalent coverage of gram-positives. Similarly, you can lump third and fourth generations together and differentiate between these 2 generations based on improved anti-pseudomonal activity in the fourth generation. Lastly, the 5th generation cephalosporin, ceftaroline, like Sweet Caroline, is reserved as a second-line drug against MRSA and vancomycin-resistant Enterococcus faecalis, but not Enterococcus faecium. I know that sort of stinks, right? It covers many gram-negatives as well as some Clostridia. While ceftaroline is not used that much, 2 classes of penicillins, the carbapenems and monobactams, are used a lot in the fight against healthcare-acquired infections. In fact, these drugs are given to treat drug-resistant or suspected drug-resistant bacteria. Instead of pip-tazo, these can be used empirically in combination with vancomycin to treat HCAIs. Once the causative agent has been identified, you will narrow coverage. Ideally, when you narrow coverage, you can put your patient on an older, cheaper drug. So let's talk about the carbapenems. They include imipenem, ertapenem, durapenem, and the star of the show, meropenem. All have broad-spectrum activity, including activity against anaerobes. Here's the difference. Ertapenem lacks anti-pseudomonal activity, but has a longer half-life than the others. Imipenem has to be given with the drug cilastatin to prevent its fast metabolism in the kidney. Meropenem and durapenem overcome both of these problems. Meropenem has been used in the U.S. market for about 10 years, longer than durapenem, and is currently the most widely used carbapenem. Lastly, we have the monobactams, the most prevalent of which is aztreonam. This is a quote-unquote weird beta-lactam in that it has only 1 ring instead of 2. This unusual structure means that monobactams do not bind to gram-positive PBPs, making it effective only against the gram-negatives. The big take-home message here is that you are only going to use the carbapenems, or pip-tazo in the setting of a healthcare-acquired infection or other documented cases of drug-resistant bacteria. Okay, let's move on to the protein synthesis inhibitors. These include macrolides, aminoglycosides, tetracyclines, lincomycins, aka clindamycin, and chloramphenicol, which we won't discuss because it isn't used anymore, and the new kid on the block, linezolid. The things to remember about these drugs is that they are all broad spectrum, and except for the situations we are going to discuss, they are usually second line behind beta-lactams. Let's start here with the macrolides. There are 3 you should know: erythromycin, azithromycin, and clarithromycin. Notice the mycin, but don't be fooled because some of the other protein synthesis inhibitors also have this mycin thing going on too. Okay, what's the difference between these 3? First off, erythromycin has been largely replaced with azithromycin, which is better tolerated. Both erythromycin and azithromycin can be used to treat chlamydia, chlamydophila, mycoplasma, and legionella, i.e. the chlamydia STIs and the atypical pneumonias. Clarithromycin is not used that much. Just keep in mind that it has better gram-positive coverage than the other 2. Next, we have the aminoglycosides, and although they are not used that much, there are a few important ones to remember. First off is the first aminoglycoside ever discovered, streptomycin, which was once used to treat TB, but is now used to treat plague, Yersinia pestis, and tularemia. Tobramycin and amikacin are used for their anti-pseudomonal activity, so you will often see these prescribed in patients with cystic fibrosis. Gentamicin, notice the spelling, MICIN, is often used in combination with other drugs to fight very nasty bacteria. All aminoglycosides are oto and renal toxic, and in pregnant women, gentamicin crosses the placenta and can cause irreversible deafness. Neomycin is used in eye drops and as a topical agent. And here is some more homework for you. Look at the antibiotics in a tube of triple antibiotic ointment. What are the other 2 drugs? The bottom line for aminoglycosides is that they are used only under very specific conditions. Moving on, we get to the kinder and gentler tetracyclines. There are 2 big names to remember here: tetracycline and doxycycline. When you hear doxy, you should think tick-borne diseases such as Lyme, ehrlichiosis, anaplasma. These diseases fall into the do not miss category, and for one of a $10 course of doxycycline, people have lost their lives. Doxy can also be used to treat chlamydia. The last 2 are clindamycin and linezolid. We already discussed clindamycin as being a good drug to treat anaerobes. Dentists love this drug because it inhibits streptococci, an anaerobic bacteria that cause dental abscesses. Just be wary of its link to Clostridium difficile infections. Linezolid is a fairly recently developed protein synthesis inhibitor that has been held back. It has a somewhat different mechanism of action, so it lacks overlap resistance that you might see with other protein synthesis inhibitors. So for the time being, linezolid is used to treat infections caused by MRSA and VRE. Next in line for discussion are the anti-metabolism drugs. Notice I say anti-metabolism rather than anti-metabolite because I also want to touch on metronidazole. Of course, the most famous anti-metabolite is TMP-SMX, used to treat UTIs as well as other infections. I'm going to break my promise about confining this discussion to bacteria by pointing out that TMP-SMX is also used to treat PCP, which of course is a fungus once thought to be a protozoan, and the DHFR inhibitor pyrimethamine is used to treat toxoplasmosis. Speaking of protozoa, metronidazole is used to treat the following anaerobes: Trichomonas vaginalis, as well as the mixed anaerobes responsible for bacterial vaginosis, Giardia, and community-acquired Clostridium difficile. Last but not least, we have what I call the central dogma inhibitors. These include the fluoroquinolones, which block DNA synthesis, and the rifamycins, which block bacterial transcription. Don't get them confused. Fluoroquinolones bind DNA gyrase topoisomerase, while RIF binds RNA polymerase. Two different enzymes, two different processes. Fluoroquinolones were used and abused, and you can thank your medical forebears when gonorrhea becomes completely untreatable. Now fluoroquinolones are considered first line only in treating pyelonephritis. Rifamycins include all drugs starting with RIF, the only difference being that only rifampin can be given either by mouth or parenterally. They are used in treating TB and as prophylaxis for Neisseria meningitidis contacts. Don't forget to warn your patients about their pee turning red. Well, that's it for the overview. Thanks for sticking with me through this. We will be filling in lots of the whys and why nots in large group session. But for the meantime, I hope this helps you sort through these drugs and begin to develop a framework to organize them. I welcome your feedback, so let me know if this is helpful and how it can be improved.